Hello, my name is Carlos.
My name is Aren.
My name is Isaac, and this is the Active Universal Car Spoiler. The Active Universal Car Spoiler Wing is a perfect addition to any car enthusiast vehicle. Not only will it redesign their car's aesthetics, but also will increase their car's performance. It stands higher in performance than any normal APR Performance or Big Country Labs product and can be mounted onto any vehicle unlike the one on the Zenvo TSR-S or the Porsche Panamera. The purpose of our project was to design a dynamic automobile spoiler wing that adjusts with wind, velocity, and speed of the car. Most automobiles are equipped with a static spoiler used for reducing drag. Making a spoiler static limits the amount of drag reduction around sharp turns or high velocities. When a wing is capable of adjusting to different velocities, it can help reduce the amount of braking time and acceleration time by either adding or reducing the air drag and downward forces. Providing an adjustable aerodynamic spoiler will help increase efficiency and performance of most cars and will be done so without a consumer having to purchase a vastly expensive sports car. The spoiler will also be universal to where it can be placed on top of any car.
The working principle of this product will have a mechanical system that will be integrated inside an aerodynamic efficient spoiler and will have the ability to change the pitch angle. In order for the wing to adjust autonomously, it will consist of sensors that obtain the angle of wind as well as its velocity. These sensors will be in conjunction with pneumatic air cylinders that adjust the angle of attack of the wing to achieve desired downforce and drag. As a final product, this autonomous spoiler should evenly distribute load transfer by adjusting its pitch, creating downforce and drag when necessary. Overall, it will improve a car's performance.
In order to determine our design and engineering specifications, we conducted quality functional deployment. Through this, we established our customer base would be anyone desiring to improve the performance of their car without having to purchase an expensive sports car. After analyzing our competition and performing calculations, we determined to incorporate a pitch sweep from 0 to 30 degrees to achieve both maximum downforce and drag. Our goal was to have 3 settings: 0 degrees for when the car is driving straight and no aerodynamic forces are desired, 15 degrees for when the car is cornering and maximum downforce is desired, and 30 degrees for when a car is braking and maximum drag is desired. Quantitatively, our goal was to achieve a maximum of 85 pounds of downforce at 55 miles an hour and a maximum drag of 25 pounds, respectively. Our aim was also to keep the mounting relatively compact while keeping the weight down as well. For this, we came up with a maximum weight of 10 pounds and a maximum volume of 62 inches by 22 inches by 24 inches. The biggest component here is the airfoil, which is 18 inches by 60 inches. After our hand calculations in QFD, we conducted finite element analysis and computational fluid dynamics simulations of our design to refine it. As a result of our CFD, we had to change some of the specifications for our assembly. Initially, it was calculated that 30 degrees would be our max angle and ideal for creating the maximum amount of drag. However, after our simulations, we determined that instead 30 degrees would be the optimal downforce angle and 45 degrees would be the used for the highest amount of drag. Our angle of 0 degrees, however, did not change, as this was proven to be the angle with the least amount of forces, making it ideal for when a car is driving straight.
In order to predict how our design would react to forces such as downforce and drag, finite element analysis was conducted by using the software ANSYS. Due to restrictions of the student version of ANSYS, the design as a whole was not analyzed, but rather the individual components that would experience significant stress were analyzed. The main components are the base and brackets. Under a certain load, we decided to focus on characteristic stresses such as total deformation, bond misses stress, maximum principal stress, and maximum shear stress. These parameters were analyzed because it will give an analysis of how the complicated geometry, along with the specified material, will behave when forces are present. When conducting an FEA onto the base of the wing, no further modification to the geometry was necessary because the results did not indicate any significant weak points that would lead to failure. Unfortunately, the bracket did exhibit poor results and redesigning the brackets was mandatory. After revising the design, they can withstand the required force. Had we had the non-student version of ANSYS, the entire wing as a whole would have been analyzed. However, this analysis provides accurate results of how the wing would behave under certain stresses.